السلام عليكم ورحمة الله وبركاته. بسم الله الرحمن الرحيم. Last time we, I think, ended up with the introduction of Bayes rule, and we had an example, and in this lecture, inshallah, we'll start with another example, and then we'll move on to one, actually not just one, it is the most important topic in this session, which is conditional independence. So let's move on with Bayes rule first. Given that I have this table, which is the marginal distribution of W, and I have also the conditional probability, conditional distribution of D given W. I want to compute this probability, which is W given dry. So this is, as you see here, this is a distribution because we have this a capital letter variable. So we expect here that we need the probability. So it will be a table for each value of W. We will get a probability. So here we have sun, we have rain, and we want to get the probability of sun given dry, which is this one. So this is P of sun given dry. And we want also to get probability of rain given dry. So that's what we mean by probability of W capital given dry. Okay, so these are the two conditional probabilities. And this as a whole is a conditional distribution now. Okay, now how can we compute this probability? Probability of sun given dry, given that we have the marginal distribution of W and the conditional distribution of D given W. Anyone? Any ideas? Can we use Bayes rule to do that? Any idea? Okay, so we are given these two distributions, okay, and we want to compute these two probabilities, which is the conditional distribution of W given dry. How can we compute each of these probabilities? Remember, Bayes rule says that probability of A given B is equal to probability of B given A, which is the reverse conditional probability, times probability of A divided by probability of B. Can we use this rule to compute these two probabilities? And let's start with the first one. Any help? How can we apply Bayes rule on this one? Saad, can you pick up the mic please and tell me? Saad? I don't hear you. Type. Someone else please. How about Yusuf? Wa alaikum assalam wa rahmatullahi wa barakatuh. That's always the case يا يوسف. امتى يعني بتقول حاجة صح يا يوسف؟ دايما بتقول حاجة غلط. Okay, go ahead. No, that's not a problem. يعني we always try together. Okay. Okay, probability of sun given dry equals probability of dry given sun. Yes. Times probability of sun. Very good. Probability of dry. Okay, do we have these probabilities? Yes. How about this one? What is this probability? One by one. Okay, so probability of dry given sun is 0.9, right? Okay, probability of sun, do we have it? 0.8, which is this one. Yes, so that's 0.8. Okay, how about probability of dry? Do we have it? You are asking me or you are answering? Which one? Hmm? How? How? And can we just add these two values? Because we have dry here and we have dry here, right? We can, right? We 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 can't. We cannot. Just because it will go over one, right? And if it happens that this is 0.5, that would be okay. Okay. طيب, let's think together يا يوسف. Probability of dry. How can we compute probability of dry using another variable? Because we don't have probability of dry directly here, right? We don't have it, right? Let's think step by step. Okay, probability of dry, we have to get it somewhere. We don't have it here, right? This is probability of W, right? We don't have dry, so this is dry is D. Okay, so we don't have it directly. So we know that we can have it by marginalizing the other variable. Okay, by summing over all possible values of the other variable, which is W, but using the joint distribution. So we have to use the joint distribution of W and dry. This one is conditional distribution. This is not a joint distribution. So we cannot add these two values actually. Of course we can add them, but that's not what we want, right? And that will not even be a probability, because as you saw, it's even more than one. So that's not what we want. So what we want is marginalizing W using the joint distribution. Now we don't have this, right? But we can use the chain rule to get this. So this one is equal to, of course, this is sum, right? So that's sum over all possible values of W. So that means that this is P of, what are the values of W? Sun and dry plus probability of rain and dry, right? Do you agree with me, Yusuf, so far? Okay, do we have both of these probabilities in the table directly? We don't have them. How can we get them? How can we get this one? Probability of sun and dry. Do you remember the conditional probability formula? So this one, the product rule, this one is equal to probability of one variable times probability of the second given the first, right? Yes, exactly. So that would be probability of sun times probability of dry given sun. Very good. Okay, and the other one is similar, right? That will be probability of what? Probability of rain times dry given rain. Okay. And we have all of these probabilities, right? Yeah, so we can compute this, and thus we can compute this one. Okay, any question about this? And of course, similarly, we can do this one also. Any question about this? Okay, first it is Bayes, not bias. Bias is a different word, Yusuf. Okay, so this is Bayes. Okay, say your question again then. What do you mean by rearranging the Bayes rule? Because we can write it in two ways, right? Depending on the order of the variables, right? But the other one, we will not have these probabilities because we don't have them in the tables. This one, we have them. Okay, that's why we choose this one. Any other questions? Thank you, Yusuf. Any other questions? So that's, I think, a very good example for using Bayes rule to compute the conditional probability. Okay, or in this case, conditional distribution even. Last time, in the last lecture, at the very end of the previous lecture, we had also another example and we didn't complete it, which is we wanted to compute this probability. This is exactly like what we did in the other example. So I will leave that to you. You have it on the slide, and it is exactly the same way we did it in the example that we went through now. Okay, so we covered this now by that. Any questions about this quiz or this example? Okay, then before we switch to conditional independence, let's just revisit Ghostbuster, knowing now something about the conditional probabilities. Before we know anything about the sensors, we don't know where the ghost is, right? In this grid. So the probability of having the ghost in any of these cells is uniform. So if we have 9 cells here, then the probability would be 1 over 9, which is approximately 0.11. So this is the probability of having the ghost in any of these cells, given no evidence, given that we didn't know anything about the colors, about the sensors. Okay, we call this the prior distribution. Why is it the word prior? Prior means before. Okay, so this is before knowing anything about the readings. Okay, so the numbers here in this grid are constitute the prior distribution of the ghost. Okay, now we also have in the game something else, which is the reading model. We know if the ghost, we know given the actual given the location of the ghost, we know what is the distribution of the readings. And last time we said that if the ghost is in the same cell, then the probability of having green will be I think 0.7. If the probability of having yellow will be 0.25 and so on. Okay, so the readings have a model, have a probabilistic model. Okay, we call this sensor reading model. So this is the probability of a reading given the location of the ghost. Okay, type. Now, if I know this model, I know that given to us. And this model doesn't change, by the way. This is the model of the game. This is given to us. And also the prior distribution is kind of given, right? Initially we start with knowing nothing about the ghost, so the prior distribution is uniform. But what we want to know is, given that we start to see some readings, what will be the probabilities of having the ghost in these cells? This is what we call the posterior distribution. Posterior means after. After what? After seeing the evidence. For example, if I click here, and I got yellow, now my belief in having the ghost here, of course, will decrease, right? Because knowing that whenever I get yellow, that's most probably the ghost is a bit far from me. So instead of having 0.11 here, I will have something that is less than 0.01. Why is that? Because now I am computing P of G given R. So here it was probability of G. That's the prior distribution, without knowing anything. Here I started to see some evidence, some readings. So my belief about G changed. Changed based on what? Based on Bayes' rule. If you remember, G given R is proportional to probability of R given G times probability of G. Type. Do we have this? Yes, this is the prior probability. Do we have this? Yes, this is the model. This is the sensor reading model. So, given this evidence, I can compute, I can update my belief about the ghost location. So knowing that this is yellow, you see here, this probability will go down because I know that the ghost most probably will be far from here. But here, if you look at these probabilities, they increased actually over these probabilities. Because I know now the ghost is maybe 2 cells far from this cell. So I will have probabilities here that are higher. How did I compute these probabilities? Using Bayes rule. Using what I know about the sensor reading model and the evidence that I observed. What is the evidence that I observed so far? It is the yellow color here. Okay? If I know something else, if I sense somewhere else, my belief will change. Third reading, my belief will change. So my belief, my probabilities will change, which we call it the posterior probabilities because they are after seeing the evidence, will change over time. Okay, this is the beauty of the Bayes rule. It allows us to update our beliefs given the evidence, or the conditional probability in general. Okay, that's the conditional probability. We do that using Bayes rule. So I will leave this video to you that will show you if I have more evidence over time, I will change my belief. Okay, so for example here, you see here the dark colors means the probability is higher. Okay, so knowing that this is green now, if I got green here, you see the surrounding area here, surrounding area of this cell having very small probabilities of having the ghost, and the outer area having higher probabilities. It's 0.04 here in this areas. Okay, and this area, but here it's less than 0.01. Why is that? It was actually uniform before. Yani when we started, everything was 0.02. After I see this green, changes. After I see more, changes even more. Okay, so now I know that it's not very close to this, so the probability will be higher here, and it will be less in the other parts, and so on. Okay, so with more evidence, I will leave that video to you. With more evidence, you will update your probabilities. Okay, any questions about that? Because with that, we are done with this set of slides, and we are inshallah ready to start the discussion on conditional independence. Any questions? Okay, then inshallah we'll switch to the other set of slides, and let me make sure that I don't make the usual mistake of not sharing the new slides. Okay, I think you see them now. Okay, so this set of slides talking about conditional independence is the core element of the entire session of probabilistic inference. So please pay a lot of attention with me, and if you have any questions, just let me know. So before going through conditional independence, let's give a quick reminder about probabilistic models. So as we said even earlier in the course, models are always simplifications. Models are not the real world. And this is actually reflected intelligently by this figure. This is you can see that this is the actual world, and you can see what we are building here is a model which is kind of a simplification or approximation of the world. It's not perfectly the world. The model might not account for every variable. It might not consider every variable in the world. It might also not consider all the interactions between those variables. Sometimes we make assumptions in our model just to simplify it, just so that we can actually run it and getting something useful out of it. So there is a really famous saying that all models are wrong, but some are useful. All models are wrong. This is true because they are simplifications. They are not 100% perfect. They are not 100% the world, representing the actual world, right? So every model has an assumption, and that assumption might not be satisfied in some cases. That's why we can say generally they are all wrong. But although they are wrong, but some of them are useful, and our role actually is to build a model that is really useful, that will help us achieving some tasks by building AI systems or AI models or AI agents. Okay, so that's the idea of modeling. Now, specifically to probabilistic models, what do we do with them? Okay, what are the applications of them? These are just two examples here, and we saw one, or we talked about one already last time, which is diagnostic reasoning. Given some symptoms, I want to know what is the probable causes. What are the probable causes? We call this diagnostic reasoning or explanation. I want to explain what I'm seeing, why I got that. Okay, so that's explanation or diagnostic reasoning. On the other side, we can do what we call causal reasoning or prediction. After getting the model, I can change some of the causes. I can change some of the variables and see what will be the effect. We call this prediction. Okay, because that's a kind of simulation mode. We change something in our model to see what can be observed in the future. That's why we call it prediction. Okay, and that's causal reasoning because we start from the cause. In diagnostic reasoning, we start from the symptoms, and we want to do diagnostic to know why this is happening. Okay, what are the causes? Okay, so these are two examples, two very common examples of using probabilistic models. Now to independence and then conditional independence. We'll start with independence. I'm sure that you are familiar with independence, but let me just go through it quickly, and then we focus more on conditional independence. So what is independence? Independence is the concept of having two variables that don't interact with each other, that don't relate to each other. Okay? And formally, we have their probabilities as we see here in the equation. If probability of x and y, if the joint probability of x and y is equal to the probability of x times probability of y, we call these two variables independent if that happens for all possible values of x and y. The traditional example here is flipping two coins. If I flip two coins, the value of each of these two coins doesn't depend of the other, right? So these are completely independent. They don't depend on each other. They don't relate at all. Okay, so if I have a variable for the first coin and a variable for the second coin, we can say that these are independent. And the joint probability of seeing both is the probability of the first times the probability of the second. Now remember that this is not what the product rule is saying. That's a special case of it. The product rule says that P of x and y, which is the joint distribution, the joint probability, is equal to probability of x times probability of, not y, it's probability of y given x. Okay? But because x and y are independent, that means that knowing x will not change our belief in y, which means that this probability is actually equal to probability of y, and that's why we have this form, that probability or a rule if for independence, probability of x and y equals to probability of x times probability of y, because that means actually that probability of y given x is probability of y, or similarly probability of x given y is probability of x. Okay, that also means that if I have if I have two variables that are independent, then their joint distribution can be represented by their marginal distributions. And I don't have to keep the joint distribution table for them. I can just have the marginal distributions, and from that I can easily compute the joint distribution. And of course, the marginal distributions are much less in size, than the joint distribution. Okay, so the joint distribution factors into the product of two much simpler distributions. So the other form, as we just said, probability of x given y is equal to probability of x. Notice that this has to be for all values of x and y, like here, of course. Okay, and we write it that way, that x is independent of y, and this is like perpendicular. Okay, so that indicates independence. And okay, before we talk about this point, any question about the definition of independence? I hope that this is clear. Of course, you studied it before, but this is putting it in our context. Independence means there is no interaction, which means that knowing one will not affect our belief or our probability of the other at all, which means that the prior probability is equal to the posterior probability. Knowing or observing this will not affect the probability of the other. Okay, now independence is a simplifying modeling assumption, and actually it doesn't happen in reality so much. So this is in very rare cases, independence. Although we tend to see some things that are completely independent, but in reality there might be some circumstances where one will affect the other. Even if in the example of the two coins, you think that flipping two coins are completely independent, right? But maybe they will hit each other, right? So if one hit the other, the value might change, right? So there might be some interaction. Maybe this is a very rare case. Okay, or maybe I can say that, okay, I will model the air pressure when I flip one, that the air pressure will affect the other, so the value of the other might change based on that. Okay, fine. Okay, that can happen. Okay, or might happen, maybe with any low probability, but it might happen. So in reality, even with these two clear cases that they might be independent, in reality they might not be independent. Yeah, so if I do them empirically, we will not get something completely, absolutely independent. Okay, so keep that in mind. Yes, sometimes of course we model something to be completely independent, but in reality it's very hard to get it empirically. And if we do the experiment, you will empirically get some relation, even if it's very weak. Okay, so independence is a simplifying assumption. Now let me show you an example. Let's say that we have a world when we want to have four variables: weather, traffic, cavity, which is التسوس في الأسنان, cavity, okay, and toothache, which is the pain in one of your teeth. So I have four variables. Now, can we assume independence between any of these two? Do you see some independence between these variables? Would be plausible or logical to assume independence between some of these variables? What do you think? Weather, traffic, cavity, toothache. Yusuf, again? Yes? Yes? What do you mean by not the other way around? Yeah, traffic doesn't affect the weather, right? But for sure there is a relation between weather and traffic, right? Can you? Yes. Okay. Yeah, but sure, but we can assume something, right? And it's logical to assume some independence here. Where are the independence relations? Where? Yes, which variables here are really independent? Are independent? Weather and traffic, weather and okay. So you can see that there are kind of two groups here. Okay, so these two together interact, of course, and probably these two also, right? because if I have cavity, I might have toothache and so on. So it seems like there is interaction here. There is interaction here, but probably there is no interaction between any of the two groups, right? So weather and cavity, they are independent. Traffic and toothache, they are independent, and so on. Okay. Any questions about this? Thanks, Yusuf. Any questions about independence? Okay, let's take an example. Quick quiz. If I have this joint distribution, so this is given to us, and we also have these two marginal probabilities or probability distributions for the same variables. Can you check if these two variables, based on the tables that we are given here, are independent or not? Can we say that T and W are independent or not, and why? I saw Faisal raise the hand before. Faisal? Why? No, say it again, sorry, Faisal. So give me an example, yes. Okay, so you're saying that if they are independent, the probability of hot and sun should be 0.3. How did you do that? How did you get that? No, just step by step, Faisal. Okay, so you said that probability of hot and sun, sorry, not hot, okay, hot and sun should be 0.3, right? How did you get this 0.3? Okay, can you tell me what should be the value in this case if they are independent? Why? If these two variables are independent, this value should be probability of hot times probability of sun, right? What is probability of hot times probability of sun? 0.3. Type. Is that the value that we see in the joint probability table? No. Yes. So that means that they are not independent. Because if they are independent, then the product of these values should be the value here. And that should be for all pairs of values of W and T. But if just one pair, it didn't hold, then that means that they are not independent. Is that clear, Faisal? Okay. Okay. Any question about this? So here we need to check independence based on the rule that we know, right? Because all of what we have here are just numbers. So if they are independent, then probability of x and y should always be probability of x times probability of y for all values of x and y. If just one pair it didn't hold, like in our case, in the first pair it didn't, then we can say that this is not independent. These two values, variables are not independent. Okay? Any questions about this? Okay, now how about this distribution? This is another joint distribution. So assume that we have this joint distribution along with these two marginal distributions. So forget about this now. Now we have a new joint distribution table. Tell me whether from these three tables T and W are independent or not. Can we see someone other than Yusuf and Faisal? محمود محتاج عزومة يعني يا محمود؟ طيب. Okay. طيب. What do you think? They are independent. Why is that? How did you know? Yes? Very good. So by that we know that they are independent? Yes, exactly. We need to check all the cases. Okay? So all the cases. For example, cold and sun. Cold is 0.5, sun is 0.6. So 0.5 times 0.6 is 0.3. So this is good. This is good. Also, you'll find that the others are also good. So for all it is holding, then that means that T and W are independent. In this case, so in that model, T and W are independent. In that model, T and W are not independent. These are two different models. Okay, one is modeling T and W to be independent, which is P2, and the other is not, which is P1. Okay. Okay, I hope that now the concept and how we check it both are clear. Another final example about independence is having the independent coin flips. If we have n independent coin flips, then we can represent the joint distribution by just n very small tables, which are the probability distributions of each. Right? Because they are independent, so we can, instead of having a huge table of joint distribution, which if, for example, n is, let's say n is 10, we have 10 coins, we flip 10 coins. If I want to get the joint distribution, then the joint distribution table, then I will have to have 2 to the power n rows here. Okay, very huge table. So that will be 2 to the power 10, which is 1024. Now, knowing that x1 is independent of x2, independent of x3, up to xn, then we just need these n tables, one for each. And each one has 2 entries only. So total will have 20 entries instead of 1024. That's a huge difference. Type, why do we only need these tables? Because any joint probability that I need to calculate, I can calculate it by just the product from these tables. So I really don't need to keep that table around. We just need to keep these very small tables around. Okay? Questions? I saw a hand, I think. Any questions about this? Okay, then let's switch to conditional independence, and please pay attention with me on that. Let's say that we have another world now, and this world we have 3 variables. Toothache, which again is indicating whether I have a pain in one of my teeth or not. Cavity at the south in that teeth, and catch. Catch means that if I have a probe, okay, the doctor or the robot here has a probe, and that probe might catch, which means that it might get stuck in a hole in your tooth. Okay, so catch means whether I will have a catch with will it stuck or not in a hole. Okay, so we have these 3 variables: toothache, cavity, and catch. Let me first ask you, do we see any independence among these 3 variables? Can you see that 2 of them are really independent, absolute independence? Any thoughts? Faisal? Yeah, but they interact, right? They interact. And I can see that one affects the other, right? Because if I have toothache, that might be because I have cavity, and because I have cavity, I might have catch, right? So there is some interaction, although it's not direct, but there is an interaction. And whenever there is an interaction, then we cannot say they are absolutely independent, right? Okay, so I think we all agree that we cannot claim any independence here. right? There is no absolute independence. Time. Now, let's assume that I told you that I have cavity. So cavity is positive here. There is cavity. هناك تسوس. Knowing that, will my belief that there will be a catch change? Knowing that I have toothache or not? يعني the probability of having a catch will depend on having toothache or not, given that I know that there is cavity? What do you think? Faisal again. But now I know that there is cavity, Faisal. That's the new evidence. I know that there is cavity. Okay? I know there is cavity. If I know there is cavity, knowing toothache will make any change in my belief that there will be a catch or not? And if I know that there is a pain in the teeth, knowing that already there is cavity, will change my belief that there will be a catch or not? What do you think, Faisal? Okay, but that's a fourth variable. We don't have this variable here. Okay, we are talking about, yeah, we are talking about these three variables now. Okay, knowing that there is cavity already makes these two variables don't interact anymore, which are the catch and toothache. Generally, they interact, but they interact through cavity. So cavity is mediating this interaction. Okay, so we can say that knowing catch, the fact that I know catch, I know cavity is known, okay, and toothache, so then the probability of catch will not change if I just removed toothache. That's the meaning of conditional independence. So catch and toothache are conditionally independent given cavity, which means that given cavity, if I know knowing toothache will not affect the probability of catch at all. Okay, Mahmoud. Yeah, we'll get to that. We'll get to that. Okay, we'll get to that. So let's first finish this. Okay, so if I have a cavity, the probability that the probe catches in it doesn't depend on whether I have a toothache or not. That's exactly what we mean by conditional independence. So probability of catch given toothache and cavity is equal to probability of catch given cavity only, which means that knowing I have toothache doesn't affect the probability at all. So that means that catch and toothache are conditionally independent. We cannot say that they are independent. They are conditionally independent given cavity. Okay? So that's the mathematical form. That's the probability form. Probability of catch given toothache and cavity is like only knowing cavity, because toothache here will not make any difference. Now, the case that Mahmoud just mentioned, if I don't have a cavity, still holds, because knowing that I don't have cavity, of course, will make will make me change my belief in catch, but knowing anything about toothache will not make that change. Okay? So in both cases, I can now generalize and say, notice that these are probabilities. This one is a distribution. We are using the capital letters here. Probability of catch given toothache and cavity is equal to probability of catch given cavity. So this is like ignoring toothache at all. And this can be also written in other forms that are completely equivalent. So I can change the order of these two variables because we say that they are conditionally independent, right? So we can switch them. So I can say that probability of toothache given catch and cavity is equal to probability of toothache given cavity. So I'll just ignore catch here because they are conditionally independent. Or the other form that I really like because it's very similar to the independence rule says that probability of toothache and catch given cavity equals to probability of toothache given cavity times probability of catch given cavity. Now imagine that we don't have this. Looking at this formula now, what does that mean? Probability of toothache and catch is equal to probability of toothache times probability of catch. That means that toothache and catch are independent here, right? Right? So that's the independence rule. But with the conditional independence, we just add to it the condition. Okay, so now probability of these two given cavity is equal to probability of the first given cavity times probability of the second given cavity. If that's the case, then toothache and catch are conditionally independent given cavity. Okay, all of these three forms are equivalent, and you can get one from the other easily using the product rule or the chain rule. Okay, I hope that the concept of conditional independence now is clear, and if not, then we'll go through an example now. This is again the form, and we write it that way, by the way. Okay, for independence we write just the independence. For the absolute independence we write just the independence symbol, but now it's conditional independence, so we say x is conditionally independent of y given z. So the conditional independence is a relation between three variables, not two. Two are conditionally independent given the third one, and that happens only if this is satisfied. Probability of x and y given z equals to probability of x given z times probability of y given z. So that looks very similar to the independence, except that we have the condition everywhere. And as we said, it is equivalent also to probability of x given z and y equals to probability of x and z. So this is like ignoring completely y if it is observed. If it becomes evidence, it doesn't matter. And as we said, absolute independence is very rare in reality. Okay, but conditional independence will be really our basic and core tool for probabilistic reasoning in uncertain environments. So this is actually what we will build our models on, not absolute independence. Because conditional independence, we can see it in real life, and we can assume it, and with that assumption, it will not be very far from reality. Because many things in our life are conditionally independent, given something else. So that will not be a strong assumption as the absolute independence. Actually, absolute independence will be rare, but conditional independence is the thing that we will use in so many cases. I know that I'm almost out of time, but I want to go through this example before we stop. Let's say that we have a world in which we have three variables. We have traffic or not, we use the umbrella or not, and it is raining or not. Okay, so we have these three variables. First, let me ask you, do we have any absolute independence between these three variables? Can you see that there are two variables that are completely independent here? Faisal? Really? You don't think that there is interaction between traffic and raining? There is, of course, interaction, right? If it's raining, most probably you will have heavy traffic, right? That will affect traffic. So I don't think there is some interaction between, there is some independence between any of these variables. These variables actually interact with each other. Okay, so it will be very strong assumption if we assume independence. But how about conditional independence? Do you see that we have a variable that is conditionally independent of the other given the third? What will be the variables here? Any thoughts? Someone other than Faisal, please. Mahmoud? Traffic is conditionally independent. With umbrella given raining. Okay, can you explain this? Why is that? Exactly. If it's raining, knowing that the robot or the agent is using the umbrella will not affect our belief about whether we have traffic or not. Right? That's only when we see it's raining, when we know that it's raining. Without knowing that might have an indication, by the way, right? Because if I see the agent using the umbrella, it might be raining, which means that we might have traffic. So there is, generally, we cannot say independence. Okay, there is an interaction. Okay, but knowing that it is raining now mediated this interaction. So it becomes clear that traffic and umbrella are completely independent, conditionally, given raining. Right? Any questions about that? Okay, again, this is a very important concept. I want you to make sure that you really understand this concept. Faisal. Okay, let's first finish this, Faisal. Let me make sure that there is no question about this. Any question about the lecture? Okay, if you still have some doubt or some you are not fully understanding the conditional independence concept, please go through the lecture again, check the textbook, all before the next lecture, because all of the following lectures will depend on that concept. All of them. Okay, so please make sure that you understand this concept before the next lecture. Okay, then inshallah we'll talk to you on Thursday. Assalamu alaikum wa rahmatullahi wa barakatuh.